In the last video, we looked at an exponential function. Now we're going to define what exponential functions are. So the exponential function with base a is defined for all real numbers x by f of x equals a to the x, where a is greater than 0 and a is not equal to 1. In general, we need the base, the number that's being raised to the x power, to be positive. We cannot consider a negative number for the base because it's not going to end up being defined for all real numbers. And we also don't want the base to be 1 because if we have 1 to the x power, 1 to any power is just 1. And so it's a constant function, which isn't interesting at all. So in general, we're looking at some number to the x power where that number is positive and not equal to 1. Let's take a look at a few graphs on one xy plane so we can compare. Here we have the graphs of three exponential functions plotted on the same xy plane. We've got f of x equals 2 to the x power. We've got g of x equals 3 to the x power, and we've got h of x equals 4 to the x power. And I want to talk about what these graphs have in common and what they don't have in common. So first of all, they have one point in common, and that point is the point 0, 1. That's because 2 to the 0 is 1, 3 to the 0 is 1, and 4 to the 0 is 1. And in fact, this is going to be true for any exponential function. It will include the point 0, 1, no matter what the base is. So that's what they have all in common. Now let's look at what happens to the graph as we take the base and we make it larger, looking at 2, 3, and then 4. When we look to the right of the point 0, 1, we can see that the larger the base, the steeper the graph is, the more quickly it's growing. And that should make sense because when we look at powers of 4, like 4, 16, 64, those are larger than powers of 2, 2, 4, 8, 16, etc. So of course, as we're taking a larger number and raising it to a positive power, we're going to end up growing much more quickly. Now, things work differently when we look to the left of this point 0, 1. We can see that the larger the base, the smaller it is, or the more quickly it goes down towards the x-axis. And the reason for this is when we have a negative exponent, we saw that that gives us something that's fractional. And so when we have a fraction, when the denominator is larger, that fraction is going to end up getting smaller and smaller. So these are the differences between the different graphs. The larger the base, the steeper it's going to grow on one side, and then the more quickly it's going to get closer to 0 on the other side. Now what I want to do is I want to look at some examples where the bases, instead of being whole numbers, are fractions. So in these cases, if we look at the bases, we've got 1/2, 1/3, and 1/4. All of these numbers are less than 1. And we can see that if the base is less than 1, then we're increasing as we move to the left and decreasing as we move to the right. The reason for this is because when we have a base that's less than 1, like 1/2, as we raise it to a higher and higher power, it actually gets smaller. 1/2 squared is 1/4. 1/2 to the third power is 1/8. So as we raise the exponent there, these are getting smaller and smaller. And when we have negative exponents, when we raise a fraction to a negative exponent, to make the exponent positive, we flip the fraction, and so these then become integers, and they are raised to higher and higher powers. So in general, if the base A is greater than 1, the graph is going to look something like this, going up to the right and down to the left. And then on the other hand, if our base is between 0 and 1, then we're going to see the opposite. It's going to be going down as it moves to the right and up to the left. However, in all of these examples, we still have the point 0, 1, and we also have a horizontal asymptote at the x-axis. So these all do still have a lot in common.